All right, good afternoon. Shall we begin? Anybody skipped lunch? No, right? Everybody is full with energy then. Okay, so we have seen register allocation based on liveness analysis and graph coloring. So given a program, let's say, how many of you know Java? I mean, a bit. It's not like you have to write Java programs of big kind today, but how many of you know C or C++? C++ rather? Okay. But C or C++ most of you know, right? So the only difference if you don't know Java for today's purpose is that each Java program is written inside a class. So in C and C++ you can have code outside classes. In Java everything is inside some class. Okay. We'll study more in detail from an optimization perspective tomorrow, but what the assignment that we would give you takes as input valid Java programs. Okay, it's actually not even Java, it's something called as mini Java. Mini Java has some restrictions. It doesn't have all kinds of Java constructs allowed. For example, it may not have a for loop, it may have only a while loop and so on. So we have a language called as mini Java, which is a subset of Java. And your programs or the assignment will take programs written in mini Java as input, and for each valid mini Java program it would perform register allocation using the algorithm that we have studied just now and give you the output of register allocation. The first pass that we had seen over there where just replace variable names with registers. Okay, and when something cannot be put into the register, what did we say we would have to do? We'll have to spill, and spilling means store the variable's value into some memory location and then load it from there, right? So there is one interesting question that should come to your mind. If I am giving you output in that form where we just replace the program with variables, variable names replaced with register names, what would we do for spilling, right? So we have special instructions omitted here. We would insert a store like instruction which will be like store into memory, but it's not an x86 or any other assembly instruction, it's just a wrapper over some Java instruction. Okay, so in Java code I have created some data structure which I am calling my memory. Okay, and when I say store at some index, it will store at that index in that data structure, in that array list, let us say, in a list, and then when I say load, it would just load some index from that memory, from that data structure, right? So that we are using to simulate our notion of memory. When you write actual x86 code, the only difference would be instead of writing store and load instructions through the API we have created here for storing and loading from that special data structure that we are calling the memory, instead of that you would emit actual hardware level store and load instructions for variables that are spilled. Okay, so that's the difference. This is just for assignment purposes. That's why we created this API around it, so that you can still see what does register allocation look like here, instead of having to worry about learning x86 instructions or any other ARM instructions and so on. Make sense? Okay, so what you would have got is a Docker file like this. If you unzip the ubuntu24.zip that's uploaded on the Google Drive link shared with you, you would find a folder like this. It has a Docker file and it has two assignments, PTA and regalloc. I don't know why they added A here. So this regalloc is the one we would use here today, and the other one is for tomorrow. Okay, so now what you would do is, I believe there is a readme as well, I assume. Now there will be a readme.md. Yeah, so what's the first step? You build, you come into this directory and then you do docker build something, right? So how many of you have successfully done that step? Many of you. If you have not been able to do due to some very specific technical reason and you don't want to spend time struggling with it right now, you can sit with one of your friends and do it together as well. Okay, only if you have not been able to set up on your laptop and you want to not lag behind and continue with the content of the hands-on, and maybe do it in some free time if you have not been able to do the first step. Okay, just sit with a friend. So docker build will create an image out of this Docker file, and this Docker file basically, if you have not used Docker, this basically says I want to involve a Debian front end from Ubuntu 24.04. So what you are getting now is an image of Ubuntu OS, a minimal Ubuntu OS, that has all these things installed. These packages are installed there: Python, Vim, Git, curl, OpenJDK, which is Java, and GraphViz, which will allow you to create these pictures of control flow graphs and interference graphs and see them. So all these would get installed in the image automatically once you run Docker build. And then there is these folders that you see over here: Winter School PTA and Winter School Reg Aloka. The last command just copies them inside your Docker image. So once you create a container, one of the next commands would be that after your build step is successful, you would spin a container. When you spin a container, basically this home student directory will get created, and Winter School PTA, Winter School Reg Aloka will be put inside that directory. All this will happen automatically once you have run Docker build. How many of you knew Docker from before? Very good. So this is useful. I mean, when you work with systems where you don't want everyone to struggle with installing dependencies and everything, you just use a Docker image like this. Okay. So now once you have got there, you would run this command. This will basically create a container named as ws25 here and put you in a bash prompt there. And we also have this -d here. -d will detach from it. Okay. If you don't detach from it, you have to work from it. On the terminal. Detach will just keep it in the background. You can still work on it from the terminal by reattaching to it, but we would reattach to it from VS Code. Okay. Now, do all of you have VS Code installed on your systems? Have you installed the extension that we had asked you to do? What was it? Dev container. What was the name? Dev container extension, right? So dev container extension allows you to attach to a Docker container. So this command will start the Docker. Okay, I have to if you are on Mac OS, then you have to start the Docker daemon using this GUI like software. So once it's there, we can let it be around, and here you just run this container. So it's there, it's on now. Let's go to Visual Studio Code. Okay, keep following with me, whatever I am doing right now. Open Visual Studio Code, and then here just press Ctrl Shift P if you are on Windows or Linux, or Command Shift P if you are on Mac OS, right? And then here just click on this dev containers attached to running container. It will tell you that these some containers are running. Just choose WS25 and you are there. Okay, so here if you see, these two folders exist, and we will work with the Reg Aloka folder today. Please, so we have, can the TAs please introduce themselves once? Just raise your hands. So we have Omkar, who is in the front, and the one behind him is Mitesh. Okay, they would be helping us conduct the hands-on sessions. So it's not just me who you should ask. Feel free to ask them. Whenever you are stuck somewhere, we'll keep roaming around, we'll sit with you. It's not a teaching session anymore. We want to make sure that you are actually practicing what we have taught. Okay. So raise your hand if you have reached this step where you have opened VS Code and you have these things you have attached to the running container. Can all of you make sure that the person on your left and right has also done this? If you have somebody on your left or right, please check with them. If they are stuck somewhere, just help them. Let's spend a couple of minutes on that. And if someone is finding an issue and their neighbors, their left right people also have not done and you have also not done, please raise your hand and one of the teaching team members will come to you. Here many of you had not set it up, right? Have you set up Docker on your systems? Yeah, now it's ready. Okay, if you find any issues, call them. Just raise your hand and whoever from us sees, they will come to you. Slash home slash student. Yeah, it's in the Docker image.
Actually, it initially went to the root
When you open the this thing, right? So just ask them to cd to slash home slash student.
Okay.
Inside VS Code, you can open a terminal using many commands. On macOS, it's Command J. Once you open the terminal, if you are in some directory which is not the same as student, then just type cd slash home slash student forward slash. Okay, just say cd slash home slash student and you are inside. Now if you do an ls here, you would again see these files: winter school pta, winter school regaloka here. We'll move ahead. I'm just waiting a couple of minutes for people who had asked doubts to get it clarified. Okay, Keith has come back, so let's continue. So now you have winter school reg aloka here. This is the folder we will be working with. If you open it here, you would see that there are several folders. Forget about many things here. You don't need to. This is the assignment that people did, and there is some auto-generated code here. Since we are not going into that right now, you can skip whatever I don't tell unless you are really interested and you want to ask about it. But there is a test cases folder here, which is important. Okay, and there is this exec.sh file that's important. So let's see this exec.sh file. This now let me make it a bit smaller. Yeah, if you see in this exec.sh file, we are just removing some things in the beginning, right? And how is a Java program compiled? A Java program is compiled using Java C. What does Java C give you? Given a Java program, what does running Java C on it give you? Dot class files, right, which is bytecode. It's the Java bytecode which is platform independent, and when you run Java followed by the name of the main class, it actually does something over that bytecode. It actually interprets or compiles that bytecode, runs it, and so on. So we'll look at that part in detail later on, but there are two steps here. So this main.java that you see is the assignments main class. This is not the test case, the mini Java test case that we are going to register allocate over. This main.java is your assignment. So if you see this main.java here, we have some code here. I am generating the control flow graph, then I am running my liveness analysis, then I am constructing an interference graph here. It's a very well commented. One of the good students implemented this assignment. Basically they have commented it very well too, but you don't need to look into its code right now, but see the structure. So this main.java shows you the structure. What's the first thing we had said? You have to construct the control flow graph. So given a mini Java program, you would construct the control flow graph here. Once you get the control flow graph, you would run a backward analysis, which is your liveness analysis. Once you have liveness information, it's stored in this result map here. And then you create an interference graph as the comment says from the liveness information. From the interference graph, you then perform register allocation. So this is the step-by-step structure of this assignment. If you are interested, you can click on anything and it will show you what does it do, and ask me if you want to really understand. But then later on, we just print the program with renamed registers to get the first output that we had talked about, where variable names will be replaced with registers and spills would be performed with our memory instructions. I want to just show you this assignments PDF if possible. Okay, I can show it on the main this thing. Yeah, so if you see, this assignment was done by somebody based on this specification. Okay, the specification was like this, that if your program, how to access liveness information, how do you specify an instruction and so on. So if you are interested, you should start by reading this. But basically this says, oh, all the registers have to be declared at the top like this. So if you have two registers, you would declare object R1, object R2 at the top. Then it says, if you say the kinds of statements that are allowed in your output program are like this. When you say A equals 10, instead you could say R1 equals 10 if register R1 has been allocated by your algorithm. Then for loading something from a register, you have to write like this. If it's an integer, then typecast into an integer and so on. If you want to store something by spilling it, you will write like this: store index at which you want to store the particular variable and the name of the variable as expression, and then you have a load instruction where you supply an index, and from that index, whichever variable you had spilled there, it will be loaded and typecasted to whatever you are using it as, right? So if this was our this is one of the programs, let's say, yeah, let's say this is the input Java program. Okay, let's see this one. Is this, yeah, so on the left hand side you see the input program, the left hand side, this is the input Java program. Now don't concentrate on Java syntax, or don't worry about it right now, but as I told you, there is a class, there are some methods and functions inside the class, and each function we will do independent register allocation. You have seen when you build control flow graphs, I hope you built it for a function, right? You did not build it for the whole program, you built it for a function. So here also we will build a control flow graph for this main function or main method here, and we would build the control flow graph for this method foo over here. Okay, so there are two methods in this test case, main and foo. And after performing, so first step would be to construct control flow graph, which we will see in the demo. And after getting the control flow graph, you are performing liveness analysis here. So this is for function foo. Function foo had these statements: a equals 5 to return t. And if you see here, these are the first 6 statements here, and this is the set of liveness analysis results after or below each statement. Is it written there? Is it the inset or the outset? Can you figure out? Can you figure out looking at this output and tell me whether this is the inset before each statement or outset? What is the meaning of in and out for liveness? In means variables that are live before that statement, and out means variables that are live after that statement, right? So if I have a statement a equals b plus c, a will become live. If a was live before, you kill it over here, right? So now, yeah, so what is this? Outset. So yeah, right. Because, and t equals d minus c, t is still live here because there is a statement return t. I think they forgot to paste it there, but there is return t here, and hence t is live. Before this statement, t is live, as well as d and e are live because they are used in future. A, c, d are live over here because a, c and d are used in future, and so on. And of course, I hope you knew, you practiced yesterday the fixed point algorithm. So if you have a loop over there, over here, you won't get your answer in the first iteration. Did you do that? Can you confirm? I mean, did you practice for some analysis? In first iteration, you will get these sets. In second iteration, you will get something else. Then once you achieve the fixed point, you have your final answer, right? So after achieving fixed point for this code, it's linear because there is no loop here. So you will get this set of live variables. Anybody who doesn't understand anything here? The live variables after each statement is what is printed here. Now based on that, they have drawn the interference graph on the right hand side, right? So let's look at some edges here. There is an edge between A and D. Why? Right. So because there is some point of time where A is live as well as D is live. So see, this is just the liveness analysis output. These are just live variables. We had constructed live ranges. How would you construct live ranges from this? A's live range starts at this statement 2 and it ends at just before this statement 5, let us say, right? So you can draw live ranges from this information, and based on that, if the live ranges of any two variables interfere, we have an edge. There is no edge between C and E, for example, here, because C is not live after this point and E is not live before this point. T doesn't have interference with any other variable because T becomes live over here, and after this the only statement is return T, in which only T is live. So T's live range does not interfere with any others, and so on, right? So this is, I hope you understand this. And after doing, so first let's try to manually do coloring of this graph based on Kempe's heuristic. Can you try? Does this, so let me tell you, this assignment was given 1 year ago. I have not verified the correctness of it. It's your job right now. So please find out, I mean, it's correct, but please find out if it's correct and be sure that if you perform register allocation using Kempe's heuristic, you would end up coming up with something like this. One variable is spilled here, D, and others are allocated some registers. Can you try that? I would like to perform graph coloring based register allocation given this set of live variables after each statement. First on paper, then we will see how do we work through the assignment. Make sure you arrive at something which is similar. Maybe you would give R1 to somebody else, R2 to somebody else, that's okay, but two registers and one spill. Now pick your favorite neighbor and make sure they also have something that looks similar to yours, or if there is a change, find out where is the mistake. Some of you have degree 1, some of you have degree 2. Try to find at least one neighbor from those. Any confusion?
There's two push statements.
Yes.
So first one you assign a register and then you push it onto the stack.
No, I don't think we have assigned registers except in the last statement. Right? So first we are just pushing all the nodes that have degree less than k, and then we are pushing those which still have degree greater than equal to k. Right?
Regardless, we just push it.
Yes. Yeah, we are pushing everything, but in some order. Non-troublemakers are below in the stack basically. Did anyone come up with the same or similar interference graph? Okay. Okay. So there is one variable that might be marked for spill.
Maybe T will be for school. I am not sure.
So we have two registers basically.
Yes.
T doesn't interfere with anything, so T can be given any register. At least as per what we have there, one variable is marked for spill. Let's check it. Yeah, so here assuming we have only two registers available, it looks like at least in this there is one variable marked for spill. Are all of you getting something similar, or is someone getting a different answer? Uh-huh. First sit with your neighbor and solve. Did you get the idea? How to do? Uh-huh. Yes. Yes. No, you don't allocate immediately as per the algorithm. You push the others also on the stack afterwards. Then you start taking one out and then allocate registers. Yes, yes, yes. So maybe first just help and discuss with your neighbor. If you're still not able to get, I'll come and help you. Yes, so if it is either, you can give anyone. T also. T, yeah, T can get anything. Huh? Yeah, one sec. D, yeah, E also can. Yeah, because it only interferes with a spill wala node, so it can get anything.
Basically, what we do is we push all the nodes which are less than k degree
First
into
two
the
stack, then the others also one by one on the
like
stack.
we remove the node
No.
completely from the tree.
No. Yeah, you remove the node and all its edges from the interference
And
graph.
then we calculate again if they are
Correct.
less than k, then we put it in the stack.
Correct.
And while popping back, we assign the register
Correct.
alternative.
Correct.
That's it.
Yeah. Not alternate. I mean, you have to check the live ranges. If they interfere, you can't give the same register. This is Kempe. Okay, can you come back for a minute towards this side? Yeah. All of you, can you have a look at the screen again? So now we are here, right? We were in VS Code, we are here, and we were looking at this file exec.sh, right? So if you see here, it's taking as input a test case. Okay, that test case here, what's the name of this test case? It's tc02.java. And where is it located? In the test cases all folder. Inside public test case, there is a file called as tc02.java. And this is the one that you have seen over there. Is this the one, or is there some difference? Same, right? The one you were working with. Let's just confirm. Yeah, a equals 5, b equals 6, t equals d minus c, and return t. Yeah. So now this code is present in this method foo, right? And now when I run this exec.sh, what does it do? It compiles my assignment, then it runs my assignment, and this redirection less than is redirecting the test case file to my assignment. Okay, so I'm redirecting tco2.java to my assignment, and then if I basically run this script, I'll get the output of running my register allocation assignment over this test case. Okay, so let's run it and see. So here, if I say bash exec.sh, or you can make the exec file executable and then do cd winter school reg alloca. Let's go inside this and then say bash exec.sh. Okay, so now let's see what do we get. We got multiple things. There is this folder recording that got generated here. So that's one interesting thing. And the second thing we got is, if you see here, we got the program after register allocation. So if you see here, for the function foo, it says registers used is 2. These are commented. So these are comments in Java. And you have spilled one variable has been spilled, and then it shows the register allocation. It says A has been spilled to memory location 0, M is memory here. Then B is R0, C is assigned R1, D is assigned to R2, R0, T is assigned to R0, E is assigned to R1. So they are using R0, R1 instead of R1, R2 like we did in the example. And then here is the program. After the comments, here is the updated program. So we had said we would declare each register at the top. Then if I want to spill one variable, I would generate this instruction alloca1, which will reserve memory for spilling one variable. Okay. Then I say store 0, 5. What is 0, 5 here? 0 is the variable that was spilled A, right? So at 0th index, you have stored 5, because what was the instruction? If you see the instruction here, the first instruction was A equals 5, right? And where has A been decided to be kept? In the memory at index number 0. So when you say A equals 5, you can't generate a register operation here. Instead, you would store 5 at memory index number 0. That's what we are doing here. Store at the 0th index the value 5. Then next statement was b equals 6. As per our assignment here, b has been given the register r0. So b equals 6 is directly replaced with r0 equals 6 like we did over there, right? Next statement is c equals a plus b. Where is a in the memory? Where is b? In R0 here, yeah. And where is C? C is supposed to be in register R1. So the instruction generated is R1 equals load the 0th index variable, which is the location for A, and add it with R0, which is the location for B. And these typecasts have to be inserted if they are to be executed as valid Java programs. That's why we have inserted these typecasts. But when you generate actual assembly, you don't have type information, you would not generate something like this. But just we wanted to run these programs for the students and show these are all runnable Java programs. That's why we came up with this typecast. Without it, Java doesn't allow you to run this program or compile this program. Then we have, let's pick one more. Let's pick the second last instruction, E equals A minus C. E is supposed to be in R1, so no, E is supposed to be in R, no, sorry, last is T equals D minus E. T is supposed to be in R0, hence R0 equals A, no, D minus E. D is supposed to be in R0, E is supposed to be in R1, so I have generated R0 minus R1 and stored the result into R0. Return T, T is in R0, so return typecast to int, return R0. I hope you see the register allocated program here in the form we have for this assignment. Okay, so this is post register allocation. So once you executed that file, what you got here is the program after register allocation. Similarly, in the main method also there is one register used, it seems, and we have alloca and all of it over here as well. Now this is what you would see on your VS Code prompt, but now more interesting thing is here. So this recording folder has an index.html file generated, which links to various dot files for the control flow graph, for the interference graph, and so on, that you can see in action on a browser. So let's spin a Python server over here. Did we have the Python command? Can somebody help me? Python followed by, it's there in your re.md, huh? Python 3 -m. Can I just have a look? Do you have it somewhere? It would be there in some readme file that was there. You have it, Python 3, yeah, hyphen, where did it go? -m http.server. Okay, current directory. -dir or directory, and then dot, the current directory, right? So I am serving this current directory here, and if you see it says open in browser, just open it from here. And no, I think we were in the wrong directory. Wait, we were not in recording. So let's go into recording, cd recording, and then run the Python, spin the Python server here, right? So now can you all look here for a minute once more? So once I basically spin a Python server, Python based server over here in the recording directory, it's there in my browser. So here is what you would see. Okay, let me zoom in. So here for each function, main and foo, you have two links, CFG and recording session. We were interested in foo. If you click on CFG, you get the control flow graph for foo. How many basic blocks are there here? Only one, because there was linear control flow in foo. We just had 6 assignment statements here followed by a return statement. So this is the control flow graph for foo. And then if you click on recording session, then you get something which is more interesting. See, here you have two things. This is the call stack. Let's look at this one, allocation visualization. So here it says we have on the stack these variables B, T, E, A, C, D. So we would push variables which have less than degree k from here. Somebody might have decided to push t also before, but in some order we have pushed b here, then t, then e, then a, c, d all have degree 2. So in the second for loop which we had in our algorithm will push the nodes with significant degree greater than equal to 2 later on, and the nodes with degree less than k before, right? So we have pushed these on the stack, and this is the interference graph for this program based on the live range analysis results. Now you can just move this here. If you move this, it says, oh, it took the first element from the stack, assigned some register R0 to it. Okay. Or it, actually some people do it from in the stack order, some people do it from before, don't worry about it. Take one element and then assign another register to it, another non-conflicted register to it. Then next you had no, I think these steps are messed up. I think these steps are not going in the right order. No, I think it's still so fine. Let's see. They have, yeah, so they are going from this direction, but the output came with D. Oh, this is not with B. Okay, fine. Then I think it's fine. It's correct. I was reading it with a wrong node. So we are going from the top of the stack, which is the right hand side. So it's correct. It's not wrong. So it's starting from the right hand side. We had pushed D at the end. So it takes out D first. It assigns it some register. You could assign it R1 or R2, any of them, or R0 or R1, any of them. We assigned R0 to D. Then we take out C from the stack. Is C conflicting with D? Yes, so we should not give it the same register, we would give it a different one, let's say R1. Yeah, so this R1 is with C, not B. The labels are a bit confusing to read. Next is A. Is A interfering with C? Yes. Is A interfering with D? Yes. How many registers do I have? Only 2. So then I have to spill A to the memory. So A is marked for spill, M0, let's say I put it at index number 0. Then I take E out here. If I take E out, it cannot be given R0, but it can be given R1. And then I take out T. T can be given anything. Let's say I gave it R0. And then I take out what is left? B. I take out B. Well, yeah, one of you asked me, what should you give to B? Is it conflict? Who is it conflicting with? A. But what register has been assigned to A? No register. It has been spilled to the memory, which means B can be put either in R1 or R0, any of them, because B interferes with a variable that does not have any register assigned to it. Instead, it has been spilled to the memory. So finally, you get R0 here. You could have given R0, R1, anyone to B, right? So this is how you can trace the allocation step. I hope it convinces you that what you had seen in the PDF is also correct. Here you can understand it step by step. So what we want you to do now is, here in VS Code, we gave TC02 as input right now, which just has a linear set of instructions. Give it something more interesting. Let's say here we have T7, where is it? Test cases all. Inside that test 7, and inside test 7 I have T7.java. So T7.java has some interesting control structures. You have an if else here from lines 37 to 42. Then you have a while loop from line 43 to line 51, and so on. So you have a bit of a more interesting control flow here. So let's see. Now let's run our script for this. Okay, I should go outside recording, execute this assignment. For that assignment, after register allocation, the code output is given here, displayed, printed here. This is a bit more complex, so you should work this out later. But now let's come to recording. Let's spin our Python server and now open this here. Now if we see here, the control flow graph for foo looks more interesting. I hope you can see there is an if branch here. So G means if G, okay. So there is a conditional here and you have a then branch and an else branch here, then there is a merge point. These circles are empty circles. Before every branch and after every branch, the student who implement this has added an empty node called as circle here, which looks like circle here. So don't worry, there is no instruction inside it. You could have removed it and directly drawn an edge from G to this BB6, basic block 6, and the other edge from G to this BB8. Then you have a merge point, and after you merge you had a while loop, right? So here your while loop starts, I believe, at BB10. There is a back edge from here. After BB17 you have a while loop, I mean an edge back to BB10, and so on. So I would like you to, by the end of, let's say, the next hour, I would like you to be able to perform register allocation over this program, at least test 7. Okay, but before, don't jump here directly. What I would like you to do is just modify one of the test cases, just add some more statements which you think are interesting. How do you define interesting? Add some if else there, add some variables which are not used in future so that they are dead variables. Is your liveness analysis able to identify them? Add some variables which have lots of interference, and so on. There is one restriction though, you cannot write random statements here which are very long. So as I said, these are not valid. This is not a complete Java program, this is a mini Java program. So you can have assignment statements like this, you can have expressions like this, ampersand or plus, star, minus, and so on. But on the right hand side, this is like three address code. So on the right hand side, you cannot have long expressions with multiple operands, more than 2 operands. So you can't say A equals B plus C minus D. You would have to break it down to 3 address code by yourself. Okay, you can assume that there was an assignment given to students before this which took valid Java programs and converted it into 3 address code form like this, which we are calling mini Java to some extent. Okay, so here similarly, if you have an if and a while, it requires you to write if and only a variable. Okay, if you write if A less than B here, the compiler will throw a parse error, because as per the language for this 3 address code, expressions are not allowed inside if and while, only a variable name is allowed. So if you want to introduce a new variable like this, what should be the type of G? Boolean, right? So in Java you have special Boolean types. So you can see here, if I introduce a variable for making my code work as per the 3 address format, I'll introduce extra temporary variables over here at the top, and if they are a Boolean variable, their type is Boolean, otherwise they are integers. So we just have integer and Boolean variables here, no other type, no float, no double, no character, nothing. So just integer and Boolean, and each statement is a 3 address statement. You can have if conditions and while loops in this code. For loops are not allowed right now. I think we have converted all loops to either while loops or if else. There is no goto here. Okay, so this is a subset of Java which has 3 address code like structure, and what you should do now is, you know from your exec.sh file that whatever test case you give as input here is the one for which this assignment will construct the control flow graph and perform register allocation, generate the program after performing register allocation. All 3 outputs will come. The program is here as we had seen, it's printed here on the screen, on the terminal, and on the browser you would get the control flow graph as well as the recording session. Recording session is your step-by-step dry run of your register allocator over the interference graph. Okay, so what you have to do is just take any of these test cases. Either you can edit the same test case file, save it, add some more instructions, as I said, some dummy instructions, some variables that are live, some are not live, if branches, loops, keep on adding more and more things to that to a given test case, and try to work out through this assignment. Look at the control flow graph. If you have any doubts, talk to your neighbors or ask us. That's what we should do for the next 1 hour. By the end of the hour, you should be able to do register allocation on your own and match your outputs with this assignment's output for a test case like test 7, which was complex. It had if else while loop, if else inside while loop, and so on. Any questions in what you are supposed to do right now? Please ask if you have any doubts, even if it sounds like a question, stupid question, oh I didn't know, how did you move into that directory? Please feel free to either call me or the TAs or your neighbors. Okay. play with control flow graphs, then move to register allocation.
Terminal nor from VS Code am I able to get that HTTP site on the local port?
What happens when you write it?
It just generates an error like this. Unable to connect.
That port is, you were telling something about the port 8000, right? Yeah, I think he has that problem. If more people have, we can announce it actually.
Okay, it's already in use now. Where did you run it before? Okay, just click on that one. It won't run. Okay, so in Linux it will have to be explicitly specified.
Okay, how do we do that?
Don't remove the image, just kill this container, the running container. Just close this now. Open up your command. Yeah, do a docker ps dash. Do it anywhere. Do docker kill and space docker. It doesn't matter. This folder won't get deleted. Just do docker kill and paste that ID. Okay. Now go back to your run. Just find the run command again. Alt R. No, the docker run command. Just do alt R. Okay, you have to paste it. So copy this. After you do that 0, just add one more. Go to the 0. Dash p 8000 colon 8000. Now attach again to the VS Code and run this server.
So it's minus p and then the port ID 8000 colon 8000. Say control shift p to attach to the container.
You did that already.
Achha, okay. cd/home/student.
Raise a look at 2 tab.
Just say bash exec, then you don't need permission for it.
Now go to the recording. HTTP.server. Now follow that link again.
Maybe we should announce this.
Yeah, I think some in Mac systems or systems it does that.
Automatically opens that port, I think. So if some of you face an issue with the Python command, It's because the port 8000 on which it's serving the output of the recording folder is not turned on for this Docker container. Okay, so what you have to do in that case is kill your Docker container using the docker kill command, and then when you write that docker run command, after 0 you have something like this, right? Docker run, and then there is some 0 here. Just add this line, add this word minus port 8000 colon 8000. We tried it on one person's system right now and it worked, and then the remaining things as it is. So add this minus p 8000 which will open up the port 8000 for your Docker container, and then the Python command will work.
First, we're supposed to work it out in a pen and paper and then verify it.
Yes, yes. At least do it for at least a couple of test cases until you get confidence. Now do the hard thing. Why are we asking you to do the hard thing if the assignment is already implemented? Because when you implement such things, you make mistakes. So you should be able to understand each step well. So if you want, we can stop the streaming right now if you want. Anyway, they are just working out. After the tea break, we'll enable it again. So, I mean, your wish.